Okay, so we're going to keep this exact same equation, but we're going to change things up a little bit. So let's say that we don't get the equilibrium concentration. But they actually give us the equilibrium constant. We can still use our math to deduce equilibrium concentration. So we use stoichiometry to deduce equilibrium concentration because we were given equilibrium concentration. But what if we weren't, but we were given enough information to find it? So we have now a 1 liter flask filled with 1 mole of hydrogen and 2 moles of iodine at 448. Very similar temperature as before. We got a Kc of 50.5, which is roughly about what we calculated, right? 51. And we want to know what are the equilibrium concentrations of H2I and I and HI. We've been given Kc. This means that we're looking at a totally different type of problem, but we are still going to be using the ice table. Now, when we are dealing with an equilibrium ice table, the units of concentration must always be in molarity. We have been given moles and volume. So what is the molarity of hydrogen?
At equilibrium or?
No, what is the initial? A flask is filled. This is the language that you're going to start seeing different language. If you fill a flask with something, that's going to be considered initial, right? Yeah. So it should just be 1.000. Moles over liters, right? Here, 2.000. 2 moles over 1 liter. We should have 0 to start with of products. The change for this particular example, again, is minus x because our stoichiometry is 1. Minus x, our stoichiometry is 1. Plus 2x because we are not only dealing with a product, we're dealing with a product that has stoichiometric coefficient of 2. At equilibrium, we're dealing with 1.000 minus x, 2.000 minus x, and 2x, or 0 plus 2x, right, which gives us 2x. Now, for us to know anything about any of these equilibrium concentrations, we need to get what value? X, right? We got to solve for x. And to solve for x, we need to utilize the fact that we know Kc, but we also need to utilize the fact that we should be able to write the Kc expression for this reaction. And again, remember the Kc expression for this reaction is Hi squared all over H2 I2 concentration. So now we have the setup. We have what we need to plug in. We also have the value for 50.5. What you will notice is that we're going to have to do some algebra, specifically quadratic equation, specifically. So if we plug in all of these values, right, then we end up getting, and I'm not going to necessarily go through all of this, but we end up getting 2x squared all over 1.000 minus x times 2.000 minus x is equal to 50.5, right? This is our expression. Now, those of you all with, solid math backgrounds might know about how to go about doing that. I am going to quickly talk about it. I would suggest that you go to my YouTube channel where I discuss in a video how to solve and use quadratic formula. But I would always suggest to use the quadratic formula in this case. If you have a graphing calculator, it's a little easier. If you have a scientific calculator, you have to use a quadratic formula. It will still work. It's just going to take you a little more work. But hopefully we remember our rules for this kind of multiplication. Remember, I was taught the whole smiley face thing. First, second, middle 2, end 2. Combine, this is going to be 4x squared. You're going to, FOIL, all of that to get you an x squared plus or minus some amount x plus or minus c, right. Now, to do that, again, that's just going to take some practice. I don't generally spend a lot of time up here going through that. That's going to be something that you're going to spend some time doing via the homework and some of the worksheets. But once you solve for this using the quadratic equation, most quadratic equations have 2 roots or 2 solutions, but realize that one of these solutions cannot be the case. Again, you cannot have a negative amount of a reactant or a product. You cannot have a negative amount of something, specifically matter in this particular case. In math, negative value, cool. But in this realm, one of these roots is no good. 2.323 cannot work because this value is 2. So we would have negative values for both of these. Can't happen. So 0.935 has to be the root. 0.935. So therefore, the equilibrium concentration for each of these is 1 minus 0.935. So it should be 0.065 at equilibrium. This one should be 1.065 at equilibrium. And then 1.87. And if we notice, these numbers look very similar to our other numbers, right? Except we just different orders of magnitude. They essentially set up the other. Again, the solving of this portion is quadratic formula, so I would revisit that. I have some videos on that. I may end up making some more, because I don't know if I have a video where it shows how to do it, a scientific calculator. I might need to go ahead and do that. So this is the type and style of question that you're definitely going to have to answer. Using enough data to find KEQ or KC, or using enough data to find equilibrium concentration utilizing KEQ or KC. And let's finish this with one example that can try to incorporate all of the stuff so far, just to make sure. Because if you lay the foundation right, then equilibrium can actually be one of the easier chapters to deal with, honestly. Question?
In the ice table, are you always going to have to use molarity?
Yes.
Okay.
For now, in equilibrium, you're going to have to use molarity. In When we get into the little acid base, you might not see that. You might not see that. So let's look at an example under, let's use a text example real quick. Perfect. This is a good one. And all right, so this 15.35 here. Mixture of 0.1 mole of NO, 0.050 moles of H2, 0.1 mole of H2O is placed in a vessel at 300 Kelvin. The following equilibrium is established. At equilibrium, they give us a concentration of NO. And they want to calculate the concentration at equilibrium of everything. And give us Kc. Now, before you start working, let's pick out some things that we noticed about this off the wham. That's a little different. What have we noticed?
The initial concentration of NO and equilibrium.
So we have two information. So we have enough information to find Keq and Kc. But what is different about this one than what I've shown you?
There's more gas product moles on the left.
Okay, maybe that too, but what else? The one that's glaring is what?
A certain amount.
Gives us,
The moles. Yeah.
it gives us moles, but no, where's water? Where's water?
It's not a liquid.
It's not a liquid, but it's on the product side. All the examples we've done thus far, your product side is equal to what? 0. Initially 0. This should not alarm you. Again, regardless of the situation, we showed that equilibrium works both ways. Regardless of the situation, whether you have some product or you don't, the equilibrium is going to shift to find its sweet spot. And we can determine which way that's going to be by looking at this. So, I'm going to help you get started here. And then see if you can take from here. First thing that you should do
Right to equilibrium.
is write the equation. Right, yeah. First thing you should do is write the equation. NO plus 2H2 gives us N2 plus 2 water. All right. Next thing would be best to do is to determine your initial concentrations of everything. So, NO initial, and I'll put a little I there, is equal to 0.10 mole over 1 liter. H2 initial is equal to 0.05 moles over 1 liter. H2O initial is equal to 0.10 moles over 1 liter. And they don't give us anything about N2, right? So our initial for N2 is 0. We don't have any for N2. And just to be thorough, we can do that. 0 moles over 1 liter. Okay, so each of these are our initial concentrations. Where would they go? They will go in our handy dandy ice table.
So we can assume for N2 is 0 moles?
It's not an assumption. Yeah, I guess it is an assumption. They don't give us anything about N2, which means that we don't have any, but that we're going to create some. We are going to create some, right? We cannot have. Okay, so this is where the conceptual side comes in. If we don't have any N2, can the reverse reaction occur?
No.
No. No. So if we don't have any N2, we have 0 reverse reaction. So that would be a great question that would throw some people off and maybe not throw other people off, is to say, based on these parameters, don't even do any math. Based on these parameters, tell me which direction you expect this reaction to proceed and why. That's an exam question. I just gave one away like that. Why should this go forward? Because you can't have a reverse when you don't have any N2. Remember, stoichiometry dictates whether we can do this or not. So we know that the number should show us moving forward first. But now, after you move forward, then you can
Go back.
You can go back, but you have to create some N2 first, right? Then you can have both, right? Because equilibrium established is when both are at the same rate. So eventually you will get the reverse to occur, just not at first, not in this setup. Okay. So the math involved in all of this, right, is real easy. They made it easy for you, right? This is 0.10 molar, 0.05 molar, 0.10 molar, and then we got 0 molar. Okay, all of these values belong here in initial. 0.10, 0.05, 0, 0.10. Now, what other information of this table do we have?
Equilibrium,
Concentration of NO, right? So we have, let's not knock this thing up. All right. I knew that was going to happen. All right. So we know this is 0.062. So mathematically, not only have we verified conceptually that we should expect the forward reaction to be occurring first, so we should have a decrease in concentration of reactants. The math tells us that that's the case too. The math tells us that concentration goes down, so we have to be using up reactants at some point. And at equilibrium, remember, we still have reactions occurring. They're just occurring forward and reverse at the same rate. Therefore, this concentration does not change. That's a very important part of it. So if we know this value, then what can we say about the change generically? Let's speak of the change generically first. The change here should be what?
negative
X.
2x.
Negative 2x. Cannot forget the stoichiometry as it pertains to the change. That's where a lot of people might make that mistake. This should be
It's the same.
the same, negative 2x
X.
plus x. Always make sure that you're denoting your signs.
Plus.
And then this should be
Plus 2.
because I'm going to be giving your credit where credit is due in the ICE tables if you set it up right. Because you may do some math stuff wrong at the end, but I'll give you credit if you got the table set up right. Okay, so if we went ahead and set all these up, we would say 0.05 minus 2x, x 0.10 plus 2x. Hopefully we see that. This is like ramping that question. That first question was basic. This is kind of ramping it up, but this is more the speed of what you need to be able to do. The question is that we need to be able to solve for each of these three, right? So part A of this question wants us to solve for 1, 2, and 3. And to solve for that, we need to use this algebraic relationship here, right? That 0.10 minus 2x equals 0.062. We have been given essentially a mathematical expression, so we should treat that as such to solve for x. So we end up with 0.10 minus 0.062 equals 2x. This is 0.038 equals 2x. Therefore, x has to equal 0.014. That's just some quick math. You can do that in a calculator. I just did it on paper. All I did was
1, 9, not 1, 4.
True. 1, 9. Yeah. Good catch. This is why you should do it on a calculator. 1, 9. Okay, so if x is 0.019, then that is our base unit, if you will, of change. That's how much we're changing by for every, stoichiometric coefficient. So we can plug that back in all of these scenarios and give us an equilibrium concentration, right? So our new equilibrium concentrations involve 0.05 minus 2x. So 0.05 minus 0.038 is 0.012, right? X is 0.019, so we got 0.019 molar. And this is 0.132, right? 38, excuse me, yeah, 0.0138. All right, hopefully everybody see that the first thing I did here, solve for x using given information. Solve for x using given information. We did not have to go quadratic here because this would have been a little too complex because of the stoichiometry. But we were given enough information to find x. Now we have to solve for x in each of these other equilibrium concentrations to give us final equilibrium concentration. And now that we have all 4 equilibrium concentrations, we can then go to the KEQ or the KC and solve for the last part of the question. The last part of the question wants us to be able to tell them the KC. That involves you writing the KC down correctly, or the KEQ, either way. KC is equal to product into H2O squared over NO squared over H2 squared. The right equilibrium expression, this is maybe where people make the mistake after the ice table. Make sure you got the ice table right. Then you got to plug all of these values in. All right, so you got 3 of them squared, and then you have KC. 653. Sure you got your order of operation right, boss.
I got 653.
Yeah, 653.68, yeah.
Yeah, it's right.
Yeah, make sure that you don't do the divide and the exponent, because you know on the scientific calculator you have to do the times 10 caret. That can get you in some trouble on the orders of operation. In the graphing calculator you can do the square button, which order of operation it beats you. You know, it keeps you from getting into trouble. Okay, 653.6. So let's say 654. All right. So 654, again, we don't have any units. What does this value say about?
Favors product.
Right, favors product. So if we got this into a vessel at this particular temperature, then we're probably going to get some product. We're going to see product at equilibrium. Now, let's say I tacked on one last part, calculate Kp, right? And the calculation of Kp at 300 Kelvin is equal to Kc 654 times 0.0821 times 300, and you don't even need the units here. Now what's delta N?
-1.
Right, -1. Negative. So raise something to the -1, which is just the inverse, right? So we end up with 654 times 0.0821 times 300 raised to -1. $26.6. So we got Kp equal to 26.6. So again, being able to do a whole problem like that is pretty standard. That's a good example, but I mean that's just one of many. You know, I put up the suggested problems from the textbook. You know, I don't really go over them that much. I might use them in the workout Wednesday. Then the homeworks, and then the supplemental stuff when you do the.
Would KP be ATM?
No, Kp doesn't have a unit, because technically the units would be liter of atmosphere. Yeah, it's still equilibrium. Yeah, it's still equilibrium, but technically it would be liter atmosphere, right? Because the Kelvin and the molar are technically gone. So sometimes it is in ATM. Yeah, that would be the last unit left. I don't think you normally see it like that. Okay, we'll try to finish up here, Le Chatelier, and then probably get in maybe one more example of the equilibrium stuff, because we want to, yeah, because we're going to want to, I think I have some problems on the one other worksheet that I wanted to show, like more stuff. So we heard a little bit about Le Chatelier when we were talking with, when we saw my man from Crash Course, and he pretty much, Le Chatelier pretty much realized that if you make a stress upon the system that is at equilibrium, it will respond to re-achieve equilibrium, and that response we can predict. Very important. So, prime example, right? If you are playing golf and the wind is blowing this way, then you are going to adjust your shot further to the right. Same if you're kicking a football, so on and so forth. If you are standing at equilibrium and you're cool, and someone in the elevator bumps into you, you will regain or force motion in the opposite direction to regain equilibrium. Same thing kind of occurs here in Le Chatelier's principle, right? And the easiest and simplest way that people have tried to describe this is, let's say we had a vessel and we had a valve here, and the valve was closed, and we open the valve. Which way do we know that we're going to have flow of water?
To the right.
Right, to the right. We know water flows this way if we open this valve. And then what will occur?
Equilibrium.
Right, we'll have an equal level of water in each of these vessels. And in one case, it's a little bit more than the initial, and in one case, it was a little bit less, right? Right? So, that would be like if we just started the reaction. Let's say we're at equilibrium, right? And we add liquid over here. And I'm nowhere near ours, so.
Those droplets.
Yeah, these are droplets. Yeah, the fact that they're being questioned just lets you know that my artistic skills have never been good. Okay, so if we add volume to that side, then what is going to occur? Flow which way?
To the left.
Right, we're going to get small amount of flow to the left
To equal it out.
to equal out, right, to balance, That's why he used the word balance with equilibrium. If we add some to the right, to the left, then we get shift to the right. Simple enough, right? You look at me like, why am I learning this? Yeah, little kid knows this. All right, just wait. All right. Now let's say I took a pot and scooped some out from this side.
It's going to flow to the right.
Right? We're going to get flow back to the right to replace what was taken. All right. Let's say that I increase the pressure over here. Let's just say I increase the pressure here. Then
It'll flow to the left. Oh, wait, is the other side closed too?
yeah, the other side's closed.
And it wouldn't do anything.
It wouldn't do anything, right? It wouldn't do anything. If you increase pressure, it wouldn't do anything because we're talking about a liquid. Increases in pressure are not going to impact the liquid in this closed system. It's not going to impact anything that's aqueous in a closed system.
If the other side is open though, wouldn't it push it out?
Not yet. Well, not necessarily, because you have to be imparting enough pressure to move the liquid. But the best way to think about it is that increases in pressure don't really impact liquid aqueous systems, but they do only temperature, right? Well, no, only adding, taking away, which is what I just showed. Adding something, taking away. Again, I'm giving you this in the scheme of some liquid vessel. We're going to transition this into actual reactions. But it's very important to know that the pressure stuff does impact when we're talking about gases. Okay, so let's take those exact same scenarios and go back into the chemical realm, and let's go back to the Haber process. Why not? Now, let's take a look at, we'll do 4 or 5 different scenarios, and I have to make something very clear because this gets confusing for people. So I'm going to give you a stress, whatever that stress is, and we'll have, let's see if we can come up with 5 of them. And then I want to know the response to the stress And I want to know, does Kc increase, decrease, or have no change in C? Shout out to the home state. So we're going to say we have, this is very important right now to say, we have a system at equilibrium. We have a system at equilibrium. To give you the equilibrium, yeah, I was about to say, we need to balance this. To give you the equilibrium expression, just for practice purposes, just to keep seeing it, because that's the best way. Keep writing. Here's our equilibrium expression, but we are talking more so qualitatively when we're dealing with Le Chatelier's. It manifests itself in mathematics if we need to go that far. When we're talking about Le Chatelier, we're talking about stress, we're talking about response. So it's very important to know that before any of these stresses occur, we are at equilibrium. We are cool. We have a rate of the forward and a rate of the reverse that is the same. We have concentrations that do not change over time. So we have balance. We have a system that really doesn't want to be disturbed. Okay. First stress. Let's say that we add H2 to the system. If we could find a way to just add some H2 into the system at equilibrium, that is the stress that we have caused this particular reaction. How would we expect it to respond? This is exactly the same as my last little water vessel setup, but we're talking about chemistry now. So we have added a reactant. How should we expect this to respond?
In addition to the product?
In addition, well, no, you're not adding product, you are creating, right? You're forming product. So you should expect formation of product. Why?
Because there are more, yeah.
Increasing the molarity?
When you say more than what?
Or the initial.
Well, we're not talking initial, we're talking, what is our initial in this case? Our initial is special because our initial is
3 moles.
at equilibrium, at equilibrium. Our initial is at equilibrium. We're no longer at an initial where we must reach equilibrium. Here I'm telling you we're already at equilibrium. So you are correct. When you add H2, the response is to create NH3. Creation of NH3 also means that you have to do what?
Increase the Kc value.
How does the creation of NH3 impact the reactants?
Because the addition of H2 is on the subscript of the equation.
No. If we're creating NH3, then what else has to be occurring at the same time?
The concentration of H3 is
We have to lose.
Yeah, no impact.
Loss of H2.
No, we have to get NH3 to form.
You have to lose into H2.
Yeah.
Correct. We have to also decrease into an H2, right? So yes, at the very split second that we add H2, the response of the system is to create NH3. But to create NH3, we have to use into an H2 in the reaction. So the response is to create NH3, which will increase NH3, and to use up the reactants, which will decrease the reactants. So more importantly, you're better off saying increase concentration of NH3 and decrease concentration of these two, right? That's the simplest, most basic equilibrium way to describe the response of the system. response to the system. Now, this brings up something that I skipped over, and I'm gonna go back to it. Here, this brings up what we call reaction quotient Q. So the reaction quotient Q is set up the exact same as the equilibrium expression. The only difference is that Q is not at equilibrium. When you see Q, we're talking about at a time before equilibrium is established, such as when this occurs, right? So let's say we were at equilibrium before we did anything. The moment we add H2, we have now went to this Q rank. We have now went to Q. Because before, let's say if we could freeze, right? We can't freeze time, right? If we could freeze time, right? If we could only freeze time. We can't freeze time, but let's say we could. If we froze time, immediately after we added H2, what would that do to the value of this expression? Think about this mathematically.
Increase it?
It would, what'd you say?
Decrease?
It would decrease it. It would, KC would be, this value will be lower than this value as soon as we add H2. Now, why? Why?
Because
Right, it's the denominator. Right, okay. So, as long as we understand it, that's a very good start. We understand that adding something here is going to make this value smaller than it originally was. So, that's a good way that I ask a question, is I could also say, and I don't want to add it in here, but I could also ask you, like here, right after the stress, I could ask you, is Q going to be greater or smaller than original KEQ? You don't have to know the value of KEQ or KC, because we don't know it right now. I haven't given it to you. All you need to know is that addition of reactant is going to drop it. Addition of product should increase. Numerator, denominator. But very important to think about Q, because Q is going to be, when Q is greater than K, something happens, and when Q is less than K, something happens, and we're going to see what happens here. We already showed what happens. The response to re-achieve equilibrium is increase and decrease of these two. So when Q is less than K, we're going to have a shift which way?
Decreases product, increases reactants.
Right. So the shift when Q is less than K is what we would say towards product. So however you want to use to help you remember that can be basic Le Chatelier, or you can also think of it in terms of Q. You got two different ways to think about it. Now, I haven't given you any numerical data on KC, but can you tell me qualitatively what happens to KC after we induce this stress and after the response?
Increase.
I guess I should say more specifically, just to give you a little clearer picture. After equilibrium is reestablished, whenever that is, it could take days, hours, months, years, who knows. After equilibrium is reestablished with a value of Kc, after our response be larger, smaller, or the same?
Larger.
And we say, we have an idea that it's going to be larger because what?
Because the increase of concentration of NH3 and the decrease of N2 and H2.
Okay. So in a basic intuitive sense, you know, that has some reasonability. That has some reasonability. But what did we say Kc is a function of?
Concentration?
Temperature. So if Kc is a function of temperature, the only thing that can change Kc is changes in temperature. Therefore, Kc
Stays the same.
stays the same. No change. Again, the response, the magnitude of the response, whichever direction, is trying to re-achieve the original value, as long as you haven't changed the temperature. The shift, left or right, in this case right, is to re-achieve that number, because what we said, our Q value ended up dropping. So to re-achieve that value, we need this to go up by a certain amount, whatever that is, and we need this to go back down by a certain amount, whatever that is, to get us back to Q equaling to K.
Okay.
And when Q equals K, you're at equilibrium. So that's one stress. All right, that's a good one. That's just one. All right, but from here it should be snowball effect. So let's say that I added NH3. I'm going to move this up a little bit. So let's say I added a product. What is my response going to be?
It's gonna
It's gonna be an increase. No.
decrease in
Still
energy
zero.
So I heard decrease in NH3, which is right.
and then increase in N2H2.
Right. So adding some to the right side is going to cause us to go left. It's going to cause a reverse to occur.
And again, no change.
So we're increasing Na into an H2. Hopefully we see that. Again, why? Because if we add an H3, Q is now larger than K. So we get a shift towards reactants. And the shift towards reactants gives us an increase in N2 and H2, and we still see no change in KEQ once equilibrium is reestablished. No change. Okay, now let's shake things up. Let's say I remove some N2. I remove N2. I'm not adding things. I'm removing things.
Quick question about this. In the system, is it an open or closed system?
It's got to be closed. Yeah, it's got to be closed.
So increasing a gas would also increase the pressure, right?
Correct,
So
but we would assume that the amount is added won't shift us that much, right? Yeah, we're going to talk about increase and decrease in pressure in some of these next ones.
But for a gas, the pressure does change the Kc value?
The pressure, Kp, again, the pressure is a function of the moles of gas, not what the gas is. Remember, the ideal gas law uses N as any moles of gas.
Mm-hmm.
So we'll talk about that in a second, because this right here, this impacts what we're Le Chavalier's, and I'm going to talk about that next. I'm going to talk about that next. Just give me 1 second. So let's say we remove N2. And again, what I should say is that in each of these given scenarios, this is the only variable that's changing. So when you say, yeah, removing gas is going to decrease pressure, true. But if I was able to keep everything constant but this,
Okay.
yeah, that would be the better way to answer your question. I'm going to show you what happens when, or how the stress, if we decrease pressure by decrease volume. So let's say we remove N2, what's going to happen?
It's going to increase the concentration of N2 and H2.
Right. You're pulling out reactants. By pulling out reactants, we've now caused Q to get larger again. We caused Q to get larger, not from the addition to the numerator, but from the taking away from the denominator. So we get a decrease in product, and guarantee you get a question like this, where it's going to give you a table, and you'll have to determine each of these. And the decreasing and the increasing again gives no change. Again, considering all other things held constant. All right. Here's some new territory. Let's say we wanted to increase the pressure, right? Which is what everybody wants to do in the scheme of athletics, right? You want to increase the pressure on somebody, see what happens. So when we talk about Le Chatelier's principle, and you increase the pressure, I have to give you this one, because this one is not necessarily intuitive, but it comes back to what Cameron, correct?
Yeah.
I'm not the greatest with that. It comes back to what Cameron was talking about when he says, well, if you increase and decrease the amounts of gases, then you're talking about changing the pressure. So let's say we do change the pressure. Let's say we have a piston of some sort and we can decrease the volume of the container and thereby increase the pressure. By definition, you just have to remember this one. The increase of pressure favors side with least moles of gas. And I don't want to go through the derivation. I think I do it on one of my videos online, so you can go and take a look at that. Think about it like this. Concentration is a function of moles over volume. When we're talking about a gas, total moles dictates pressure, not moles of each thing, right? We don't care about the identity. So when we decrease the volume, we've done some changes to this K equilibrium values, more so than we've done before, right? Because adding, and removing hasn't changed the volume, right? Adding, and removing means that our moles over liters is still constant. When we change the pressure by decreasing the volume, then we get a little bit of mathematical difference, and that mathematical difference is accounted for in this reaction by this whole delta N. That's why delta N matters. So in this particular case, our response, if we favor the least moles of gas, the response to this is going to be what?
Increase in NH3.
Right, increase in product. So we're going to increase in NH3 and decrease in the rest. Holding everything constant still, we are back to no change, no change.
So by least moles, you mean total least moles of products and reactants?
Right, total pressure favors side with least moles of gas. Again, we can have reactions that are heterogeneous, like the limestone reaction, right? If you increase pressure in that limestone equilibrium, you force it back to the side, right? You force it back left. The last stress, and again, you'll see these types of problems again in your worksheet. But the last type of stress, let's say we're going to decrease temperature. So we already said temperature dictates K, but how? How? We got to go back to some old stuff from Gen Chem 1. Maybe you didn't get to it, very much of it. We're going to get to it after acid-base equilibrium, but we had to talk a little thermodynamics now. To be able to determine how temperature impacts equilibrium, you need to know the enthalpy. You need to know the enthalpy. Delta H. You need to know the enthalpy. And you need to just know the sign of the enthalpy. Excuse me, whether it's negative or positive. And just so that I'm staying consistent, I don't know, is the Haber process endo or exothermic? Exo. All right. So if it is exothermic, what does that mean for the sign of delta H?
Positive. It's negative.
Negative. Negative. Exothermic release, right? The negative means you release energy just like combustion. So we're releasing, we got an exothermic, which means that heat belongs where on our chemical equation?
On the right side.
On the right side. So now temperature and heat correlate. So you got to know enthalpy to be able to answer this last one. You have to be able to place the heat used or released in the right place. Now we say if we decrease temperature, we know that decreasing the temperature means that energy is going to be transferred.
From the right to the left.
So if we decrease the temperature, we need to replace a product effectively because we're now cooling the system down. So to replace this product, to decrease the temperature, you're actually going to shift this reaction to the right. You're going to essentially force it to replenish the heat. So we're going to see an increase in NH3 and a decrease in reactants. So if you were a chemical engineer, such as Haber, when you were first coming up with trying to make this ammonia, and you knew it was exothermic, and you wanted the product, then what would you want to do?
Decrease the
You would want to make sure that the reaction vessel you were doing this in was cool. Cooler. The cooler, the more you force it to the right. Right? We know that we force it to the right because temperature is essentially taking away heat. Decreasing temperature is essentially taking away heat. To replenish that heat, which is what the reaction wants to do because of its nature, to replenish that heat, it's going to keep pushing it out. Like, man, where's the heat going? That's going to create more and more NH3 because you can't get heat without the other product. And if you are wanting to create NH3, this is perfect for you. Now, how does that impact K? We said that K now has been impacted because we've done something to the temperature. How would that impact K?
It would make it larger.
It will make it larger, right? It will make it larger. It will increase K because we are increasing the amount of stuff on the product side, which is on the numerator. So from an application standpoint, right, why do we care about this? Other than it just being equilibrium. A chem engineer wants to know what temperature affects the reaction progress. Because if we were trying to make ammonia for fertilizer, for bombs, for whatever, then we want to do any utilization of the concept of equilibrium to get us more stuff more efficiently, faster, cheaper. So how to apply this? This is being applied all day, every day in the chemical industry. Is equilibrium. If you were a chemical engineer and you were impacting equilibrium and causing less product to be made, then you wouldn't have a job very long. Because then I'm like, man, you don't know chemistry, right? So if you try to get a chemical engineering job, you come from my class and you mess this up. Don't tell them. You came from me. I taught you right. increase. Let's say you heated it up, you decreased heat. Generally, when we talk about industrial processes, what's the first thing that you know is going to happen? It's going to get warm, right? Stuff working, metal, whatever. So Haber originally, and everybody else who did this, originally thought that cooling this down was the best way to go. They knew that. They knew that cooling it down was the best way to go because of equilibrium. But refrigeration is expensive. I don't know if you know that, but the Carnot cycle, everything, refrigeration as a process is energetically expensive, which costs money for energy, for electricity. So what they decided to do, and this is just a little aside, this is not necessarily equilibrium, what they decided to do is they decided to use ammonia's boiling point to remove ammonia from the system as it was being made. Essentially, number 6, the 6th stress, remove ammonia. And you would tell me removing ammonia is going to shift it to the right, which is going to increase ammonia and decrease products, which is what we want. Using up reactants, increasing products. We're not changing KEQ. So instead of just decreasing the temperature, they decided they wanted to decrease the temperature to get ammonia gas to condense, fall, collect, and force the equilibrium to help them. So that's what eventually occurred. After Haber came up with it, some other guys got involved, Germans, Americans, and eventually the process that's done now, they make some billions of tons of ammonia every year just for fertilizer purposes. The process, essentially, as the ammonia gas is created in this big system, right, these big vats, as this is created, they dump the temperature down extremely low. This turns into my funny looking droplets. It collects in like a bin, and then the system up here is now feeling the stress of losing product and replenishes product. So you're essentially forcing it, right? It's kind of like the idea of like holding the carrot in front of the horse, right? They're going to keep going forward because they think eventually they're going to get to it. The chemical system thinks that eventually it's going to reach equilibrium. But if you keep stealing the product, in this case, then you can do that, right? And there's certain situations where you might want to do the opposite. You might want to add products, something like that. But the chemical engineer is the one who came up with the idea, you know what, maybe we should condense it. The chemist only kind of cared more so about the K, EQ, and things of that nature. But you will see another table like this. You will have to give me the response. You will have to give me whether KC changes or not. And you'll also potentially have to give me a why, a written portion of why do you expect this to be the case. Another thing that you want to have here is low pressure, right? You want low pressure here. You want increased pressure here as well. So you want high pressure, low temp to essentially effectively give yourself a lot more product. And let me take a look at one. Hopefully it's up here already. If not, I need to go back and get this for y'all.
For pressure, it says this favors the side with the least amount of moles
Of gas.
of gas. What if both sides have the same amount?
Then pressure does nothing. Then pressure does nothing, right?
For number 6, when you remove the NH3,
Mm-hmm.
won't that also decrease N2 and H2?
Yeah, that's what you, yeah, I just didn't finish right. Yeah, it will, it will. You're gonna decrease your products. So, yeah, if increasing pressure doesn't do you any good unless you have one side or the other with at least less or more. Let's see, where's my equilibrium supplement material? Yeah, this one is huge. This thing is 58 pages. This has got a lot of good stuff in it. A lot of good stuff. But I mean, I would only go to the areas that you feel like you are having problems with, right? But I wanted to do another, see, a lot of this Le Chatelier stuff at front is good, right? If you decrease temperature, then how would you shift? Le Chatelier is up front. I wanted to use more of the mathematical ones. Okay, yeah, let's go here. I wanted to show one example of the quadratic just because I need to. Nope. I want them to give me KQ. Okay. All right. Here you go. Number 4. This is about a very basic example, but I wanted to show this, and I'm going to work this quadratic all the way out. It should be a pretty simple one. It is, yeah, it is. So they've given us hydrogen and sulfur to create hydrosulfuric acid. H2 plus sulfur to give H2S. We got gas, we got a solid, we got gas, I think, right? Well, I guess you can make sulfur gas too, though. No. Yeah, they have sulfur as a gas? I can't see.
It says solid.
No, they got it as a solid. That's what I thought. That's what I thought. Doesn't matter for this particular question, but sulfur is a solid. Sulfur is a yellow solid. It's what you smell in eggs.
When they rot?
No, it's what you smell when you boil them. Like the smell of an egg when you boil it and open it, what's in the center? It's a ton of sulfur in the yolk. That's the reason it's yellow. Yeah. So when you smell that smell, that's no, it's not rotten egg. That's actually sulfur. But sulfur is good for you.
Is there a correlation with that in cholesterol?
So the cholesterol is in the
yolk
white part, is in the other part,
I
right?
thought it was in the yolk as well.
Or it's in the yolk as well, but I mean, it's not what is the sulfur. No, cholesterol, sterol is a big organic molecule. Yeah. The sulfur is the metal portion of it. Okay, so they've given us amounts placed in the 2-liter flask, allowed to reach equilibrium, and I need to zoom out even further because no, I don't. They gave us KEQ, and they want us to calculate the concentration at equilibrium. Okay, so ice table, always jump to that first when you see these. Do not get in a hurry and write down 0.6 right here, because that's the mistake people are going to make. They're going to write down 0.6 when they see it. It needs to be 0.6 over 2. So H2 initial needs to be 0.6 moles over 2 liters. S
1.4 over 2.
Why is it just wrong?
Why?
Because it's solid.
Solid, yeah.
The reason is that the concentration of solid sulfur will never change, right? Because the density is an intrinsic value. So we can't put that in there. That was the reason why I wanted to zoom in and make sure it wasn't a gas. Okay? H2S initial is 0. All right. So 0.6 over 2 is what?
3.
0.3. 6, 12, 18. 0.3. All right. So our initial concentration, 0.3. We are not worried about S. So whenever you see me put a dash like that, that's just saying that it is not useful to us. It's irrelevant. You don't want to put a 1 there either, because it's then you want to subtract something from it, right? All right. Stoichiometry tells us that the change here is going to be minus X. The change here is going to be plus X. We're not worried about sulfur. Another reason we're not worried about sulfur is because we have more sulfur than we do hydrogen. So hydrogen is our limiting reagent to begin with. That's another reason that this problem works out, but you don't have to really think about that to get this right. So then we end up with 0.3 minus X and X. We need to write the equilibrium expression. KEQ is equal to product H2S over reactant H2. We don't have any exponents because we have a 1-to-1-to-1 stoichiometric ratio.
What you at 14 equals?
Yeah, well, I just wanted to show the equilibrium expression first to make sure that you wrote it down right. But yes, this all equals 14. So this isn't a quadratic, but still, it'll give us the idea. We have been asked to find the concentration of H2 at equilibrium, which means that we have to find X, right? And we can find X by multiplying. We end up with 0.3 times 14 minus 14x equals x. So we get 0.3 times 14 equals 15x, and therefore we have x equals 0.3 times 14 over 15. Just algebra, or they say algebra. 0.3 times 14 divided by 15. 0.28. 0.28 molar is the concentration of our product. To get the concentration of reactant left, it's 0.02 mole, right? We have very little H2 left. Our equilibrium KEQ was given to us as equaling 14. Greater than 1, product should be favored. And here, we're able to subtract from X. Again, if I ask you for H2 at equilibrium, you can't just write down this value, because this value is not H2. This value is the value for H2S though, right?
So a question like that with a solid will never ask us anything about the solid.
But it's going to be there to trick you so that you put 1.4 over 2 and then end up with a KEQ that's wrong, and then end up everything past that is no good, right? I would just make sure that you head to the YouTube. I cover a lot more of your complex problems, and I cover the quadratic stuff. For those that are not familiar with quadratic stuff, you're going to want to get familiar very quickly and check out those videos. I need to go back and see if I did one with a scientific calculator. If not, I will do one of those to show you how to use the quadratic formula. Because the quadratic formula, unfortunately, is a place where you can make a lot of mistakes. Doing it on the graphic calculator, I also show how to do that as well. It's a lot more simple, a lot simpler. Again, I had a test finished up. Pretty much the grade spreadsheet is pretty much finalized up to the lab reports. I still y'all take a couple looks at those and give some feedback. So that's what we'll do Thursday, because Thursday's live shouldn't be extremely long, but we'll take the beginning of that to run through the test real quick and give some feedbacks on the lab report so that the future ones can be correct if they are currently not. And then if you got any questions about, you know, workout Wednesdays or styles of problems you want to see done or answer keys to some of the worksheets, let me know, and then I can add those to the playlist for the future. And I guess I will see y'all Thursday.
Question about the lab report?
Yep.
So, how do we react to iodine? Do we have to use the same converting this one here to get hydrogen?
You mean? No, to determine the order of reaction with respect to iodide, these two experiments have hydrogen peroxide as the same concentration, so they go to 1. It cancels out.
Right. I understand to get the order. I'm just saying because how you got the concentration for hydrogen peroxide in the first place, 0.034.
Oh, I did that from the standardization. Y'all didn't do that. That's the reason why I wrote it up there. So y'all didn't do that. That was part A on the experiment.
Yeah.
I did that for you.
Okay.
Okay. So all I did was, all this is that the H2O, the reaction of H2O2 and sodium thiosulfate is 2 to 1.
Okay.
The titration I did was giving me an initial and a final, and this volume of Na2S2O3 was what I used in that stoichiometry you just showed me. That reaction, that stuff at the top.
Okay.
Yeah. All of this was the amount of milliliters I used, this was the concentration of the sodium thiosulfate. Here is the stoichiometry 1 to 2, and then I used 1 milliliter of hydrogen peroxide. So in that 1 milliliter, that's titration, which you haven't done yet. We do that in acid base. That titration told me exactly how much H2O2 was in that 1 milliliter. Because hydrogen peroxide out of the store is mostly water, it's 3%. So it's mostly water. So this titration would tell me exactly how many moles of this were there. I put that number of moles over 1 milliliter, that's this first number, 0.508. So that's the in-bottle concentration of peroxide.
Okay.
Once you went in that bottle and took 10 mils
Okay.
and poured that into this beaker with 140 worth of other crap, you have now done M1V1 equals M2V2. I really hope they're doing that in Gen Chem 1. If not, I need to talk to people. Okay, so M1 is 508. V1 is 10 mils. M2, which is what I calculated for you, is unknown, and V2 is 150 mils. If you do the math here, you see milliliters cancels out. You're left with M2 is equal to 0.5808 molar times 10 over 150. Because you're now left with molarity. So M2 in this case with 10 is what, 0.034?
Yeah.
Okay, so this is for every 10 milliliter experiment. Because all your experiments are 150. So this for every 10 milliliter. All I did was divide this by 2 to get for the 5. Right, because it's half as much.
Okay.
And you assume that, you know, it's uniformly distributed. So now, you have double concentration between the 2 experiments. If you look at the time average, it should be about double the time, right?
Yeah.
Because I did this calculation using y'all's data.
Yeah.
And you see that it's about 2 to 2, and which means that the order is going to be 1.
Right.
Now, for iodine, it's the same thing, but you can calculate the concentration of iodine on your own because we're not doing a titration.
Right.
You know what concentration of Ki was.
Yeah. It was 0.008.
And then we can just.
No, 0.005. What was it to begin with? It was 0.05. What was the stock bottle of KI? 0.05 molar, and then you have to do this exact M1B1. What was the? You have to know what the stock of KI was, and that's in here.
I don't need the stock of KR.
Yeah, it showed you what was the original concentration.
I didn't print the whole thing. I just print the
Concentration of KI is,
Yeah, it's over here. 0.05.
105.
So it should be 0.05 times however much you put in there, 25 over 150.
Okay.
And then times 30 over 150, or 50. Yeah, you're using 1 and 3. So you're doing the two different concentrations for experiment 1 and 3. So it should be 0.05 times 25 over 150, 0.05 times 50 over 150.
Okay.
And that will give you these two concentrations. So it should be 0.05 times whatever, like I said, over 50.
Oh, I think that's how I got 40 zeros right here.